Today, we're going to look at a variation of the optimization problems that we've been doing. And this is going to be called constrained optimization. Before, we were just taking a look at a function, one variable or two variables, and looking for local maximum and local minimum values. Today, we're going to add something else to that problem. So let's suppose that we want to find the maximum and minimum values of the function f of xy is equal to x plus y. Now, right away, we can see that there are not going to be any local maximum or minimum values of this function. If I want the maximum values of this function, I could just make x and y infinite. If I want the minimum values of the function, I can do the same, make x and y infinite in the negative direction. So there are no local maximum and minimum values of this function. So what we're going to do is subject this function to some constraints. So let's find the maximum and minimum values of f of x equals x plus y on the circle x squared plus y squared equals 9. So we have set up two functions. One of them we're going to call the objective function, the one that we want to maximize or minimize. So f of x is our objective function. This is the one that we want to find the maximum and minimum values of. And it is being subject to some constraints. We can't just pick any values of x and y. They have to fit this description. So this is our constraint. So I picked this problem because we can visualize this problem. We can imagine what this problem looks like. We look at the objective function, f of x equals x plus y, and we know that the objective function is a plane. So we can see that the objective function is just a plane. And so let's take a look at that graph. So f of x equals x plus y is a plane. Let's take a look at the contour diagram of that plane. This is a very risky maneuver because I want to draw my x and y axis, and eventually I'm going to be drawing a circle. So this never goes well. Always draw the circle first, but here I am breaking my own rules. So the objective function is a plane. We have no maximum and minimum values on a plane because the plane just goes forever, increasing and decreasing. But let's draw the contour diagram. So the contours are going to be x plus y equals some constant. So the contours are going to look like x plus y equals some constant. So we can write them as y is equal to negative x plus k. So it's just going to be a bunch of lines with a slope -1. So I'm just going to draw all the contours with slope -1. guess I don't need all the contours with a slope of -1. Because already I'm getting tired of drawing contours. So here we have a bunch of values or a bunch of contours on the plane. Bunch of parallel lines because we're dealing with a plane, and we can imagine the plane above this. We should write down the values of the constants. So these are going to be different values for the function. So notice that the k, the contours are the value of the function equals some constant. So through the origin, this is where f of x is equal to 0. If my y-intercept is 1, there's my 1. Should have spread them out more because I picked a 3 for the radius, but that's all right. What we want to notice about these contours is that each contour represents a different value for the function. And we can see which direction the values of the function are increasing. So we're getting larger values of x as we go up along this direction. We can combine this with what we know about gradients. We know that if we go perpendicular to the contour, that will be the direction of maximum increase. So the values of the function are increasing as we go in this 45 degrees above the x-axis. That's our direction of maximum increase. All right. So we've got all these different values of x values of f of x. And we can see we're not going to get unconstrained. Our objective function will have no maximum and no minimum. So without constraints, our objective function has no maximum or no minimum. We don't rein this in. No maximum. And this just keeps going on forever that direction, so we'll have no minimum value of f of x. Oops, f of x, y. Unconstrained, no maximum value of f of x, y, no minimum value of f of x, y. So, I did want to point out, thinking about the things that we know, let's put the gradient on one of these contours, because it's going to be the same because we got nice boring plane. The gradient of f will point in the direction of maximum increase. We can see that the direction of gradient of f should be 1i plus 1j. Should go perpendicular to these lines, these contours. The contours are lines with a slope of -1. So the gradient will have a slope of 1, which is a delta x of 1 for a delta y of 1. We can also just calculate that. The other reason that I picked x plus y, it's really easy to calculate the gradient of f. Our intuition told us that this is what the gradient of f the direction of the gradient of f, and our calculation confirms that. Fx will be equal to 1, and Fy will also be equal to 1. All right. So the contours are all these lines with a slope of -1. We know we get higher values of the function if we go in the direction of 1, 1. And if we go in the opposite, -1, -1, we'll have maximum decrease. Let's look at the constraints. So if we can pick any values of x and y, we will not have a maximum value or minimum value. But when we put this constraint, x squared plus y squared equals 9, we're saying we only get to pick values of x and y that sit on the circle. So now if we add in the constraints, that the constraint means that these are the only values of x and y we get to pick. They have to fit this description for reasons. So So there is the circle, x squared plus y squared equals 9. And we want the maximum and minimum values of the function. If we look at different values of the function, different values of the function show up as parallel lines. So different values of the function show up as parallel lines with a slope of -1. So here's where f of x is equal to 0, but we know we can get a larger value of f of x by going in the direction of 1i plus 1j. So here is a larger value of f. So eventually, we're going to pull these parallel lines, and and this is also the direction of increase. Here are increasing values of f. And eventually, we're going to run out of space on the circle x squared plus y squared is equal to 9. Eventually, we're going to get a contour running tangent to our constraint. And that's going to be our maximum value of f. This is going to be where our maximum value of f. Because once we get past this point, we are no longer going to have values on the plane also on the circle x squared plus y squared equals 9. So this is where our maximum value of that's going to be the maximum value of f subject to the constraint g of xy equals 9. If we go in the other direction, we know that f is decreasing if we go in the direction of -1i minus j. And once again, we'll just wait till we get tangent to the circle. And here we'll find our minimum value of f subject to g equals 9. Remember, each contour represents a different value for the function. We want the highest and lowest values for the function that are still in contact with this circle. So the reason that I picked a circle and contours that were just going to be slope of -1 is that we can see where these 2 points are going to be. We're looking for these 2 points. And we know that these 2 points are on the line x equals y. Because we're running tangent to the circle with a slope of -1. So they're going to hit the circle at a 45-degree angle, where theta is 45 measured from the positive x-axis. So these points will happen when x equals y. Right now, we're not using calculus, we're just using geometry. And that's why I picked this example. The maximum and minimum values happen when x is equal to y. And so, of course, I didn't leave myself enough space. I'm like, well, I filled this space in here. And I was thinking to myself, man, I really need this space, don't I? And then I'm like, oh, well, just keep writing. But if x is equal to y, I can just write 2x squared is equal to 9, and then take the square roots. So x squared plus x squared is equal to 9. So 2x squared is equal to 9. So x is equal to 3 over the square root of 2, plus or minus 3 over root 2. Since these points happen when x is equal to y, our maximum value must happen when x is positive root 3 over 2 and y is positive root 3 over 2. And the minimum value will happen when x is negative root 3 over 2 and y is negative root 3 over 2. Oh, sorry, negative 3 over root 2. Then the maximum happens at positive root 3 over, sorry, I have a trig class, so everything's root 3 over 2. Positive 3 over root 2 and negative 3 over root 2. I won't be able to fit it. Any questions? So what we were going for is a place where our objective was tangent to our constraint. We need a more general way to figure that out so that we don't have to rely on a simple geometry problem to get at our answer. What we wanted was the objective to be tangent to the restraint. Sorry, the constraint. And you could probably guess that the gradient is going to show up because I brought the gradient up previously. Notice that, remember that the gradient is always going to be perpendicular to our contour. So our contour is our direction of no change. Our gradient is the direction of maximum increase. So here's what we're going to be doing. So if we want to maximize a function subject to g of x, y equals some constant, I want the contours of f to be tangents to the the curve g of x, y equals some constant. So we go perpendicular to that. I want the gradient of f. Like, I spelled gradient wrong. We can also think of this as the gradient of f going in the same direction as the gradient of g. I want the gradients to go in the same direction, but they don't need to be the same value. So I just need one of these to be a multiple of the other. So we just say gradient of f is equal to lambda times the gradient of g. So that's a lowercase lambda. So when I say gradient of f is equal to lambda times the gradient of g, we just want the gradient of f and the gradient of g to be going in the same direction. Lowercase lambda is a scalar. And this is just requiring that the gradient of f and the gradient of g, both vectors, are going in the same direction, but they can have different magnitudes. Same direction, but different magnitudes. So I multiply by a scalar. So now what we need to do is take our proposed process and apply it to a problem to which we already have the solution, our circle and plane problem. So let's revisit our circle and plane problem. If we want to maximize and minimize f of xy is x plus y subject to g of xy, which would be x squared plus y squared, equals 9. I want the gradient of f to be a constant times the gradient of g. That would indicate the two gradients are going in the same direction. I want the gradient of f to go in the same direction as the gradient of g. So the gradient of f, we know, is going perpendicular to the contour. And the gradient of g will be perpendicular to the contour. And I just want to find the point where those gradients line up and go in the same direction. So let's write down the gradient of f. So the gradient of f, I need fx is going to be 1 and fy is going to be 1. So the gradient of f is 1i plus 1j. I also need to look at the gradient of g. I'm not worried about the 9 part. I'm worried about what the function is doing. So the gradient of g, so gx is going to be 2x plus 0, and gy is going to be 0 plus 2y. So the gradient of g is going to be 2x times I plus 2y j. Now I want the gradient of f to be a constant multiple of the gradient of g. So I'm going to set the equation gradient f is equal to lambda times the gradient of g. That means I want I, now I'm going to put the 1, 1i plus 1j is equal to lambda times the gradient of g, which is 2xi plus 2yj. If I incorporate the lambda in, it would look like 2 lambda x I plus 2 lambda y j. If these two vectors are equal, then the components must be equal. So this would mean that 1 is equal to 2 lambda x and 1 is equal to 2 lambda y. So if vectors are equal, then their components must be equal. Now we just have to figure out what this tells us about x and y. Secretly, we already know that this means that x is equal to y, and we can see that. If 2 lambda x is equal to 1 and 2 lambda y is equal to 1, we can solve this by saying that 2 lambda x must be equal to 2 lambda y. Lambda just is a constant. It's just a scalar multiple of, it's just a scalar multiple that we put in, because I want the gradient of f and the gradient of g to go in the same direction, but they don't need to have the same magnitude. So the lambda will stretch or shrink the gradient of g so that it matches the gradient of f, because that'll capture the same direction information. So if 2 lambda x is equal to 1 and 2 lambda y is equal to 1, that means 2 lambda x is equal to 2 lambda y. And that tells us that x is equal to y. Just as we had foreseen. We're like the emperor. I can't draw an emperor. He's not a stick figure because he's wearing a robe all the time, so I just have to draw kind of like a. And there's a hood on it. The Emperor is such from Star Wars, such an annoying know-it-all. Every time someone tells him something, he's like, well, yes, I know. Just as I had foreseen. But then he has that whole ruthless angle, so no one wants to come up and say, hey, Bob just crashed your car. Yes, I know. Dude, I'm lying. I was talking about you lying to me. You know what I mean? I guess what I'm saying is that there's no way that that guy had kids. He's really annoying. Any questions? So what we have is a process for optimizing a function subject to a constraint. I want the gradient of my objective to go in the same direction as the gradient of my constraint. Once we solve that, that doesn't take into account the actual value of the constraint. Notice that this was all based on the function f of xy and the function g of xy. We haven't brought the 9 into it as well. But once we have this restriction, x is equal to y, we can take this and plug it into our constraint to find actual values for x and y. So now that we have x equals y, we can take, this is what we get from the gradient information. Take the info that you get from the gradient information, take the info from the gradient equation to the constraints. We haven't used the fact that g of x is supposed to be equal to 9, so we can clearly tell that we are not done with the problem. If you're given a piece of information in a problem and you haven't used it, you should stop and think there's something missing. So now we'll take this given information from the information from the gradient equation, we'll drop that into the constraint and we'll get some actual numbers. So since x is equal to y, just like we did before, that means x squared plus y squared is equal to x squared plus x squared is all equal to 9. So here's where we can get that x is plus or minus 3 over the square root of 2. And then when x is 3 over the square root of 2, y is 3 over the square root of 2. The last thing we would need to do is figure out which one is the maximum and which one is the minimum. But we can just figure that out by looking at the values. If we're not sure, we can plug them into the function and figure out which value of the function is bigger than the other one. So here's our mathematical process. And the reason that I like to go over the intuition first is that's the thing that will help us remember what to do. We don't want to have a note card that says grad f equals lambda grad y on it. If we have a note card with that written down on it, then we don't understand what we're doing. And it's the same thing in algebra class. If in algebra class, you need to bring a card that says m equals y2 minus y1 over x2 minus x1, then you don't understand what's going on. You're trying to rely on things like formulas when your understanding should tell you it's the change in y divided by the change in x. A lot of times we get too focused on things like formulas. But what we need to do is take a formula and make sure that that matches with our intuition of a situation. That way we'll know what formulas and what equations we actually need to carry around with ourselves, carry around all the time. Any questions? So once again, gradient of f is equal to lambda times gradient of g, meaning gradient of f and the gradient of g are going in the same direction. The lambda just represents the different values that they might, or the different magnitudes that they might have. This makes sense because we're going for, I have the gradient of f, and I want the gradient of g to be going in the same direction. So gradient of g is always going to be normal or perpendicular to this circle. So I want to find out where those line up. So this is a good picture to carry around to help you remember constrained optimization. Gradient of f is equal to lambda times gradient of g. Any questions? Comments? Snide remarks? How's everybody, okay? All right, so this is the end of week 6. Up next is going to be week 7. The next thing on our agenda is going to be a major shift in what we're doing. So I want to take at least a couple of days to do some catch-up work. So this week, it needs to be all about making sure that everything in chapters 12 through 15 is on solid footing. So that's what I want you to focus on this week. The next thing that we're going to talk about is integration. That's our next big topic, integration, because those are the two big things that we talk about in calculus, differentiation and integration. Then, of course, the one big thing that we're talking about in calculus, lest we forget, is just infinity. Calculus is when we first start thinking about infinity. Infinitely small, infinitely large. We really need to get a handle on that. But the next particular thing that we'll be talking about is integration. So next week is all about catching up and also making sure that we understand integration. We're going to start with by reminding ourselves what integration is about in a single variable. We're not going to be doing a lot of techniques of integration. That's for Calc 2. And theoretically, we've already suffered through that. Or I mean, we've already enjoyed going through all our techniques of integration, especially like trigonometric substitution, because that's our favorite. But we want to get in place, make sure that our thinking about integration is in place so we can move it forward, because this class, multivariable calculus, is all about taking single variable calculus and trying to apply it to functions of more than one variable. Any questions? Comments? Deep thoughts? Just fear. Fear is the mind killer, so don't do that. All right, that's going to do it for today. I will see y'all on, that's going to do it for this week. I'll see y'all on Monday. If you have questions, send me an email. I'll be in office hours tomorrow, but I'm not just sitting around waiting for people to show up. So send me an email and a time, and then I can make sure that I'm online at that time. All right, now that's going to do it for today. That's going to do it for this week. Everybody have a good weekend, and thanks for playing.
Thank you, Professor.